All right, so today the major thing we're going to do first is what is called fluid force. Now let's keep it real simple. Does anybody here ever swim? Whether it be in a swimming pool or the ocean. Does anybody have access to like a really deep swimming pool? You know, I know over at Stanley Park, at least they used to when my kids were younger, we'd take them there, and I think it was an 11-foot pool. And you know, that's pretty deep for a public pool. And what would be funny is the lifeguards and stuff, sometimes things would get dropped, you know, kids would drop stuff at the bottom, and they didn't like going down and getting them. Because that's a lot of work and stuff, and it'd be kind of funny because I have no issues when it comes to things like that. I have some interesting things I can do in the water that other people can't. Like I can lay on a bottom of a pool. My record is 90 seconds with my lungs completely full of air. I sink right to the bottom instantly. And I can lay there, and I just let the bubbles go every now and then, which always scares the heck out of lifeguards when they see somebody laying at the bottom of a pool, you know. But why is it when you are at the bottom of the pool that it feels like your head's being crushed by a bazillion pounds of water? Why is that?
Water's very heavy.
Because you're being crushed by a bazillion pounds of water. It's exactly that. Water's really heavy. And we don't think about that. And so what you often do, right, you do the thing with your nose to pressurize your ears. Does anybody here, or has anybody here ever dived? Scuba dive. So you understand that the deeper you go, the pressure is huge, and that's why you have to constantly depressurize. I used to dive a long time ago. I dove in college, and it was kind of an interesting thing. A typical 3/8" neoprene wetsuit, you use either a 23 or 24 pound weight belt to compensate for the buoyancy of the wetsuit. If I did that, I would have a difficult time making it back to the surface. I used to use a 12 pound. Because I did things that were supposedly impossible. I could touch the bottom of a pool wearing a wetsuit without a weight belt. That's supposed to be impossible. I have adamantium on my bones, like Wolverine. It is comical, but when I swim, I can't swim on the top of the water. I've never learned how to do proper leg kicks because half my body is always underwater. So when I'm swimming, I swim more like this. So I just learned as a kid to swim. I just swam on the bottom of the pool and then came up for air. When I was testing to get certified, you remember getting certified, you had to do the 10-minute float?
I didn't get certified.
Oh, okay.
Yeah,
Well, they kind of want you to do that so you don't drown when you go out there. But you have to do a 10-minute float. You're supposed to just, in the pool, just float. In case, in other words, you're out in the ocean and there's an accident, you have to be able to float. So you do the 10-minute float. They passed me anyway, but my 10-minute float was I'd stand on the bottom of the pool, go up, grab my air, go back to the bottom of the pool, because it's physically impossible for me to float. I'd have to tread water so furiously to stay at the top of the pool. So I just stood at the bottom and would jump up. But I always was very fascinated with the whole aspects of water and the weight and the pressure and how that works. So here's what we're going to do just for fun. We're going to fill up this room with water. We're going to fill it up with water, okay? We won't tell anybody. Now, can we measure the weight on the floor? Now, I want you to think, real simple terms, can we measure how much weight? That's, by the way, fluid force, that's just the weight, isn't it? Can we measure the weight? Yeah, the only thing we would need is the water density. And by the way, water density is a constant. You do not have to know the density of any liquid. If you were in a physics class and you're doing this problem, you probably have a sheet of different substances and the different densities. Water density, it's about, and the one they usually use is, believe it or not, pounds. Pounds per what? Cubic foot, which is kind of an odd thing because you don't think of water in cubic feet, but it's kind of a convenient one. Most calculus books will use 62.5, by the way, because 62.5 is exactly 1/16 of 1,000. And it makes numbers really, really nice and easy to work with and calculate. 62.4 is not very convenient. So what I do is I say we're going to use a liquid of the following density, and I'll just use a nice round number, 100. 50, something that's lighter than water or heavier than water. That's not important, but it's the density. We talked about this last day. Remember I said there's 6 types of density? There's mass per unit length, area, or volume, but there's also weight per unit length, area, or volume. We're going to use weight per unit volume as the density of the liquid because the mass won't be useful to us. We can't measure force if we only have the mass. We need its weight. So regardless of what we're doing, if we wanted to figure out then if it's this per cubic foot, then I only need to know how many cubic feet of water I have. Do you agree? So when we fill up this room, that's probably several thousand cubic feet of water. That's really heavy. Now think about that. That's really heavy on the floor. That's a lot of weight on the floor. So where are most swimming pools?
Underground.
Or at least ground level. Would you agree? Most swimming pools are probably ground level. Have you ever seen a swimming pool up high in a hotel?
Yeah.
I have. And it's always interesting. Why would you put a swimming pool way up high? Because the amount of weight is so much more than a regular story would be, right? But that's the thing. So you say, well, that's easy. Well, I don't need calculus for that. You're right. We don't need calculus for that. Because we're going to fill up this room with water, and we know the floor is going to support it. What we'd like to know is, what's the force on this wall? Or that wall, or that wall, or that wall? Is the force on this wall the weight of the water? No. That's only the force on the floor. Now think about that for a moment. This is an interesting concept. How do I figure out the force against the wall? And so if I filled up this room with water, or let's say this room kept going and went all the way to the other side, and I filled it up with water, does that affect the force against this wall? How far back the room goes, do you think?
No.
No, in fact, if I said, let me build a little pony wall, a foot away, I'm going to save water. I'm big on saving water. So I'm going to build a little pony wall 1 foot from this wall, and now I'm going to fill that up with water. Will that be the same force on this wall as if I went all the way across the room?
Yes.
Yes. Yeah, the wall doesn't know how far it goes in this direction. The wall only understands what's making direct contact. Now, at first, that kind of defies common sense, doesn't it? But again, I'm not talking about vertical, I'm talking about horizontal. So it's only the water against the wall that I'm measuring. So here's what I want you to think, like this. Okay, so let's say that's the level of water, and I have submerged something, and let's say the thing I've submerged, and I'm going to do these horizontally. This is often referred to as a lamina. It's kind of an odd word. But I'm going to submerge something. By the way, I don't care how thick it is. I want to know what is the force here. And now, I'm not talking about the whole way. This is all water or liquid. Do you think sideways changes anything? Or do you think it's vertical that changes?
Vertical.
Yeah, because the water, right, the force of the water, if this is really, really deep, what part of my wall is experiencing the most force? The top of the wall or the bottom of the wall?
Bottom.
Probably the bottom of the wall. So the deeper I go, the more force there's going to be. So what we're going to do is, so let's take an arbitrary slice of this thing. Now, if I measure this way, that's called the depth. And we mentioned this last day. We generally measure depth as 0 is at the top, and we increase going down, right? Because nobody, when they're swimming, you say, I went really deep today. I went negative 20 feet today. That just wouldn't make any sense, would it? For divers, you always measure it in the depth you went, not how far from the bottom of the ocean you were. You measure it from the depth, because the deeper you go, there are different rules. If you go very deep, you are limited to how long you can dive, and also how long you have to wait before you dive again. There's certain dangers that you face, okay? And I'm not going to go into that. That's why you get certified, because you learn these things. But if you're not very deep, there's no danger. So this would be the depth. Let's call that y sub I. And let's call this thickness delta y sub I. It's the ith one. And for lack of a better name, let's call this the length, for lack of a better name. Okay? Now, you notice it's not a function of x that I'm looking at, it's only y that I'm looking at. I'm looking at this way. Now, the length may be in terms of x, but I need this guy here. Now, what are the units we're looking at? Well, depth, how is depth measured?
Meters.
It's a length unit. Do you agree? It's not an area unit, it's a length unit. So we could be meters, we could measure it in feet, we could measure it however, but this is definitely a length unit. I have the area of my slice, and I have the density. What is the density? We said density is, what we're going to do is weight per volume. I would like to know the force. Well, weight is force. We sometimes don't think of it that way, but weight is the simplest force we know of. Okay, when you stand on a scale, that's the force your body is emitting on the scale due to gravity. How do I put these three things together to get force? Should be kind of easy. How can I put these three things together and get force as a result?
Multiply them together.
Multiply all three of them together, exactly. Because then I have length times area, which is now volume, multiplied by weight per volume. So what we're going to do is always, we're going to multiply the depth times the area times the density. And this gives us the fluid force. This is for anything on planet Earth. This is how you calculate fluid force. Weight times depth times density. So in this case here, the density must be given. I must be given the density of my liquid. And by the way, in this case, density would usually be a constant. Usually. There are situations where it's not. We'll do those next semester a little bit. But for right now, we would think of density as being a constant. I'm going to have a liquid that's constant. Now, by the way, that's not always reasonable. Okay? That's not always reasonable. Does anybody ever buy orange juice? You know, like already mixed orange juice? Not the stuff in the frozen can. So you go down to Costco or Trader Joe's or something, you get your orange juice. You can see at the bottom all the pulp is settled, can't you? So what do? You shake it up. Before you shake it up, is that thing of uniform density? No, it's way less dense at the top. And by the way, that's all things will separate over time. So let's assume that you shook it up. So whatever we're working with, this liquid has been shaken up. Because we need it to be uniform density. If density were variable in this case, that makes the problem so much harder. It makes it so much more difficult. It's not that it's wrong, it just starts becoming way too much. So given this, then I need to figure out the force on this slice right here. So the ith force will be the depth times the density. I'll put the density first, and I'll call that the L of y, if you will. That's going to be the force. So if I want to know the total force on the entire lamina here, I integrate this thing. But I'm integrating it with respect to y, aren't I? There's no integration with respect to x. You can't be doing things sideways. That won't work. Okay? So I'm going to do a simple example of one. It's one of my favorite examples because I think it's easy to interpret. Okay. In San Diego, there is a pipe that it's around Point Loma that goes out to the ocean. Does everybody know what I'm talking about? And it's, I don't know how far, it's like 3 miles or something. It's a sewage pipe. We pump raw sewage into the ocean. But we go way out in the ocean so it's not harmful to us. Yeah. That just sounds terrible, doesn't it? So this thing is really long. And let's say, we'll keep it real simple. Let's say that it is half full. It's never going to be completely full. That just really won't work. It's half full at any given time. Now, what happens is you close it off periodically. You don't leave it open 100% of the time because you put stuff in, you take stuff out. But it's closed off, let's say, at one end. And maybe it's closed off at both ends for a while. This thing could be 10 feet long. It could be 10 miles long. I want to compute the force here, because that has everything to do with the integrity of what I'm building. Does it matter how long it is? No. It would matter how long if I wanted to know the total weight on the bottom of the pipe, but not on the front of the pipe. Just like we said, the weight against the wall has nothing to do with how far it goes horizontally, but it does have to do with how big this is. Now, this is actually what they look like. They're huge. They're big and round, and they're kind of nasty. I come from a family of contractors. I'm the only one that's not, so I'm very familiar with the construction process my whole life. This is called a culvert, and back in the day, every house built had one of these leaving the house. And it went underground just outside of your house into something called a leach field. Anybody ever heard that term? And it's basically raw sewage underground. And the problem would be is if your pipes get backed up or something, you got the guy coming out there with the steam shovel and they're digging your backyard up and they have to get to it and fix it. It's pretty awful. But I grew up in an area where every single house had this. And nowadays I don't think they do things quite the same way, but we still have sewage pipes, by the way, going from like your kitchen into the street and collecting there. That still happens because we just did a huge remodel during the pandemic and they had to clear out all those lines and there's always stuff in the lines. Now, they're not this big around. They're probably more like this big around. But this would be, you know, for the city of San Diego, something huge. So let's say that I have got this thing filled. It's got not water. So let's say the density, is 75 pounds per cubic foot. It's a little more dense than water. It's got, you know, it's got crud. Let's just leave it at that, okay? And let's say that this pipe here, I don't know, let's say it is a 10-foot diameter. It's huge. Now, I'm doing this in English Standard. I have, on the quiz that you're going to be doing for this one, I gave you a metric. It doesn't make any difference on the calculus part. The calculus is going to be exactly the same. It's only going to matter at the end of the problem when you give units. So my units for this answer would be pounds. What would my units be if it were a metric answer? Newtons. Newtons, which is why no one wants to do a metric answer because no one's familiar with having. You can't give kilograms for an answer. Actually, there is no question I can think of, believe it or not, that kilograms would ever be the answer to. It's actually not possible to get mass as the answer to the question unless we're only talking about the mass of an object, not this. No, we have to get force as an answer. So our answer here is going to be in pounds. If we're doing this metric, our answer is going to be in newtons. No big deal. Okay? So I would like to know how much force is there. So, in other words, this is it. Now this is real life. Okay? And in Calc 3 we do this all the time. You're given the situation, you're asked to answer the problem. I would love the job where they hand me a sheet of equations or things or integrals. Could integrate these, at the end of the day we're going to pay you. You know, give you a paycheck. You're like, cool, I like that job. No, your job is, here's a situation, figure it out. It's called problem solving. You're never going to be given an equation to solve or an integral to evaluate. You're going to be given a situation and you got to set up the problem. So I'm giving you the situation. We have a really long pipe. The length clearly doesn't matter. It's 10 feet in diameter. It's half full of a sludge that's 75 pounds per cubic foot. What's the force on this end? So, okay, I can do that. It's probably just a simple equation. No, it's not. It's going to involve an integration. Do you want to go ahead and close it? It's going to involve an integration. I don't have any functions here to integrate. I don't actually have anything. I kind of need to set up a problem. Well, it is two-dimensional, isn't it, what I'm looking at? So I have a circle. It's two-dimensional. Do you suppose it would be wise for me to come up maybe with an XY plane? Where do you want to put the X and Y axis? By the way, all choices are correct. Not all choices are practical. Well, if I put the x-axis at the bottom, then I could call that 0, except we talked about depth. Oh, that would make it kind of confusing. So what's a better choice for the x-axis?
In the middle.
Probably running right through the middle. Well, then where should I put the y-axis? Right here?
No. In the middle.
Why would it be advantageous for me to put the axes running through the middle of this thing? By the way, I just said all choices are correct.
Because it creates a four quadrant.
Well, think of it this way. The equation of a circle, you guys all know how to do a circle, right? X minus the x coordinate squared plus y minus the y coordinate squared equals the square of the radius. But if my center isn't the origin, that makes the equation of the circle just a little more complicated, doesn't it? And now trying to solve things and integrate things can get a little bit dicey. But if I put the center of the circle at the origin, then isn't it just simply x squared plus y squared equals r squared? Which is a way, way simpler equation to work with. Now remember, you are the engineer, if you will. You are the mathematician. You get to set up the problem any way you want. So you would choose a way that said, you know what, I'm going to minimize the difficulty of this problem. So I think that would do it. So if the diameter is 10, then what would the equation of this circle be? Five? 25 would be 5 squared. Okay? So just like before, what we're going to do, take an arbitrary slice. That's our depth. We're measuring it from the top down. So our depth is going to go from 0 to what? Well, if depth were negative, we have two problems. One is all of our answers would be imaginary. that would not work, by the way. We would get imaginary numbers for all problems. I don't want to do that. No, it's going to be 5 because we're 5 units down. Remember, depth is always measured from the top down. It's not measured. Now, if I put the y-axis here, I could think of it in reverse, but it would make it so much more complicated. So this is my depth. Now, from here to here is clearly x. So what is it all the way across?
2x.
That would be 2x. Beautiful. So what is the area of that slice? I'll say the ith area is clearly 2xi times delta yi, which presents just a teeny little issue here. And you dealt with this last semester when you did volumes by slicing, probably. You remember your base is a circle and your cross sections look like, you know, rectangles. You guys remember doing stuff like that? Well, the problem was you always had something in terms of x multiplied by delta y or something in terms of y multiplied by delta x. Every problem had the same original setup. I can't do a problem with x and y at the same time. Which one governs the variable that I have to use? The left or the right?
Right.
It's the delta. I can't write delta y in terms of x, but I can write x in terms of y. So I'm stuck with that guy. So how do I remedy this?
Use the equation.
Use the equation of the circle. If x squared equals y squared plus 25, and I'm calling positive x that width, then what would x equal?
Square root of y squared. 25 minus y squared.
25 minus y squared, and it would be the positive square root because we're calling x that positive distance. So a better term would be then 2 square root of 25 minus y sub I squared times delta y sub I. Now at first that looks kind of scary, but this is actually going to not be bad at all. So I have my density, I have my depth, I have my area. I can now state the arbitrary force. Now I'm going to remind you of why we do things in a certain order and also the things we can skip. So the ith force, the force on that slice, will be 75 yi square root of, or sorry, lost my 2 in there, so. And the range of values of y we just said was 0 to 5. This is the force on that slice. So here's what we're actually saying. We're going to go back to Calc 1 for a moment. Calc 1 we'd say now the total force can be estimated by, it cannot be equal to the sum of these. It would be estimated because this is a finite sum. The sum from I equal 1 to n of this and then we could say the actual force equals the limit as the norm of the partition approaches 0. I'll just put dittos of all that stuff. That's called the Riemann sum. Then we wrote the integral. But what does the integral look like? It looks like that. This is Calc 1. This is how all problems are done. You start with the setup, you write the Riemann sum, you do the limit and all that, and then in the end you say the force is this. And I'm just going right back to this, to this. So if you remember in Calc 1, hopefully, once you understood the process, I like going right from here to here, personally. In my class, once you get the process I show you, just go right to the integral. Because you know all of this is going to be the summation, I'm going to take a limit. You never evaluate the limit. The limit is the definite integral. That's the definition of the definite integral. So we always found the arbitrary slice, and we went right to the integral. You guys okay with that? That's what we do. That's what we do all the way through calculus and beyond. But we need to figure this part out before we can integrate. Now I have this integration. That's not that bad. It looks kind of scary at first. Do you know any functions that look like this? No. So what technique from Calc 1 would you use? u substitution. My argument is 25 minus y squared, and the derivative of my argument is sitting right out there. So this is perfect for u sub. And by the way, u substitution is still a very, very common method. You're going to learn way more. In fact, there's infinitely many more problems that are not going to be u sub than are. But if something looks like a u sub, always take advantage because it's probably the shortest route. So if we let our u equal 25 minus y squared, then du dy would be negative 2y. And then I'll remind you, why did we do this? This is not a quantity. No, what you're actually doing is you're saying the integral of this is equal to the integral of this. And the integral of this is u, and the integral of this is negative y squared. I'm sorry. I should go back. It's 25 minus y squared. Because you're already putting it inside an integral, you don't need to write the integral symbols here because it's already living in an integral. So what this meant was you are replacing this instruction with this instruction. So at this point, it's sitting right there, isn't it? What do I do with the 75 though?
Bring it to the front.
Yeah, pull it up front. Get it out of the way. It's just sort of in our way right now. And here's what I'm going to do. I'm going to write this as 25 minus y squared to the 1/2 power times negative 2y dy. Oh, wait a minute. I need a negative 2y dy.
Just add up. Yeah.
Can I do that?
Yeah.
Because I got equal. Have I done any calculus yet on this? No. No, but this is wise to do what I just did because this is where the substitution is coming from, right? It's going to be u to the 1/2 du, which is a very, very friendly integral. But I need to have the chain rule factor. Now, a reminder, I don't assume anything except that you can integrate. My experience, because I've literally 40,000 students calculus, that most people do u substitution terribly. I mean, they actually have a wrong answer to every definite integral they ever attempt. But I got the right answer. No, what they'll have is 2, 3, or 4 different numerical answers, and one of them might be correct. That's the equivalent of filling in all the bubbles on the multiple choice. You can't have any wrong answers and say my answer is correct. No, you can't have, and my answer is 0 or 1 or infinity or D and E. I'll put them all down. That way I'm covering all my bases. This is equal to this. I haven't done any calculus yet. But when I make my substitution, do we agree with that?
Yeah.
Very friendly integral. How about that?
No, you have to change it.
No, because that not only will give me a really small negative answer, it won't even be a similar answer. No, there is no situation that exists in a definite integral that you can leave the old limits of integration. Remember, the answer to your question is numerical. When you write a definite integral, the answer to that is a number, and numbers cannot equal 2 different quantities at the same time. So the absolute rule, not a suggestion, the absolute rule is if I'm changing the variable in a definite integral, then I also have to change the limits of integration. And that's actually the easiest part. It's just the part we all forget to do. So I like to do it like this. I have sort of like a shorthand. As y ranges from 0 to 5, what's u going to range from?
25.
25 to what?
0.
0. That's all I got to do. Anything else is absolutely in every conceivable way incorrect because you will get a wrong number. And what's worse is people will then say, and now it equals a different number, which then equals a different number still. I usually get like 3 answers to these. Don't just get one.
Can you explain that again, that last part?
Yeah, I will go back a little bit because this is a section we're going to be doing a lot of this right now because we're going to get into higher levels of things really, really quickly. I also have published notes that I go into detail because in all the things you do through the calculus sequence, this is one of the most common, but it's an area that if we're not really careful, we can give contradictions unknowingly, and we don't mean to. So when I do this now, I'm saying whatever numerical value this one had, I'm pretty sure this has the same thing. But whatever numerical value this one has, which I don't know how to calculate, I'm saying it is equal to the numerical value that this one has. And this one hopefully is easy to calculate. Agreed? Hopefully this one's easy. what's the antiderivative of u to the 1/2?
2/3 times u to the 3/2.
So 2/3, but I already had a negative 75, so what would that be? Negative 50?
Yeah.
And when I go from 25 to 0, get out your calculators. Is this answer going to be positive or negative?
Negative.
You sure? That minus that? No, it's going to be positive. Because the first, you're going to have 0 minus. Now, what is 25 to the 3/2 power? 125. So my answer is what? I'll put it up here. 6250. Very nice engineered number. That's not the end of the problem. Units.
Pounds per cubic foot.
What are we finding?
So like what?
Force.
Newtons.
Do I have a third?
Joules?
Just pounds. Just pounds. Well, first of all, we know it's English standard because the problem is English standard, but which part of this is force? Just the pounds. This is where we get a little bit confused. We used density, we used depth, we used area, we used all of these things, but my final answer has to be force. That's why I know that's the final answer. Is that, everybody okay with that? That's why I know it's the final answer, because this is the only part that's just force. Now, it turned out the numbers were really friendly. So I'm going to go back really quickly and remind you guys of something. The substitution itself, I'm not really worried your ability to substitute. Most people are pretty good with that. But it was the whole thing about the limits change. Because I want to show you, in Calc 1, we really want you to do everything. We want you to do things that are not necessarily even efficient, just to make sure you're always following the procedures. But by the time you get to Calc 3, a lot of times you're going to do the substitution. Just so you know, when I do this problem, when I get to this point, I just evaluate this. I don't ever actually substitute, ever. I've done, I don't know, on the order of closing in on infinity antiderivatives. It is absolutely trivial at some point to just do this. It's actually really, really, really simple once you've done a lot of problems. I don't ever physically change the variable. I'm too lazy. Because at this point here, I'm just giving you the antiderivative in terms of y, because you can't. But I'm going to show you why you can do that, and I want to remind you. So let's start with a fairly simple problem. Let's say the problem is, 1 to 2, and I've got 4x squared plus 3 to the, 4th power, and I'm multiplying it by 8x dx. Let's keep it really simple. Okay? Keep it really simple. My chain rule factor is sitting right there. You all agree? Mm-hmm. So this is Calc 1. So in Calc 1 we say, let's let u equal 4x squared plus 3, then my du is 8x dx, which means within the integration I am replacing this instruction with this instruction when I replace the variables. You do all of your substitution at one time. It is not mathematically possible for you to have two variables in the integral at the same time at this point, because one would be the dependent, one would be the independent. That's an absolute impossibility, and it absolutely gives a very, very different answer. You don't write this down. In Calc 3, you're going to do problems like this all the time. This is Calc 3. Calc 3, you do integrals with multiple variables. These are not even similar answers. They're not even close to each other, but x and y are both independent variables in this case. We can only do one independent variable. So if we have two variables in the problem at the same time, it automatically means they both had to be independent. Don't write this down. You can actually do that, because the only variable is x. Y is treated as a constant. So every time you ever did a substitution and you left the u and the x in there at the same time, you realize your final answer isn't even similar to whatever you wrote. It's absolutely incorrect, because it means you should have factored the x part out of the integral, which gives you something unrelated completely. No, in Calc 3 we do this because we have multiple independent variables. So now I want you to forget that. Yeah, when you get to that point in the video, just close your eyes. It all makes sense when you get there, okay? So when I do this, I'm a bit squeamish about the limits of integration. Is it legal for me to just simply find the general antiderivative? Could I just do this problem first? Is that legal? Absolutely, that's what I tell people to do if you're not sure. It's more work, but it's absolutely correct. So ignore the limits of integration. Let's just find the general antiderivative. So this would then be u to the 4th du, which is what, 1/5 u to the 5th plus c. And now I'll substitute back. Does everybody agree that that's the correct antiderivative?
Yeah.
Yeah.
Hopefully. Now, and I remind people in Calc 1, you don't always substitute back. In an indefinite integral, your answer is a function. You substitute back because your answer should be a function of the same variable that the question was in. In a definite integral, your answer is a constant. So you never, ever in any context, do you go backwards and substitute back. You never do that. When you change the variable, you cannot go back to x. It's not possible. There is no route going backwards. This is a number. So we just evaluate this. So, and definite integrals you're going to find as you go on are going to be far more common than indefinite integrals. But this is my safety net. Now let me ask the question. Because what I'm showing you is not efficient, but it is correct. Right? I found the antiderivative, and now I'm going to evaluate that antiderivative from 1 to 2. Everybody okay with that? Okay, so let's do that. By the way, plus c. This is not a trick question, and this is not just an afterthought. You were told don't bother writing the plus c in your antiderivative. Why? If you're in my class, you can't answer, because you know the answer. Don't answer. See it?
It cancels.
If I put the plus c here, then I evaluate this at 2, it'll be something plus c, and then I evaluate at 1, it'll be something plus c. It means all values of c will still give me the same numerical answer at the end. Do you understand that? It wouldn't matter what value of c you chose. There are 2 places in your mathematical careers. The second one will be in about 2 weeks in my differential equations class. There are 2 areas in your mathematical careers where you actually get to select the value of c. Since all values of c will give you the same answer for a definite integral, what value of c do you think you might want to choose?
0.
0. C isn't 0 in an antiderivative, but all values of c in the definite integral give the same final answer, so you choose c to be 0. You were always told, oh, just ignore the c, drop the c. No, you can't ignore the c. Just choose c to be 0 in this case. In a general antiderivative, can I choose this to be 0? No, I have to leave it there because if I don't have initial conditions, this could literally be any real number. I don't know, so I leave it. But over here, it wouldn't matter what c is, it's going to cancel in every conceivable situation, so I don't bother with it, I just make it be 0. Now, when I evaluate this, this is going to be 1/5 times, what's that, 19 to the 5th power? And then, I'm sorry, minus, does that look right?
Yeah.
16 plus, okay, now whatever that is whatever that is. I'm not worried about, get your calculator out. So we agree on a final answer. Simply doing your integral off to the side and then coming back and doing this is always legal. It's the most amount of work a problem can take, but there are going to be many problems that we do even this semester where you may prefer this route because the level of complication within the substitutions, we're going to be doing substitutions that are way beyond this. Way more complicated than this, starting next day, by the way. We're going to be doing things involving limits with infinities in our integrals that are so much more complicated that a lot of you will say, you know what, let me do the general off to the side because there's so much going on. This is always legal. Now, what if I want to change the limits because I want a more efficient problem? I want to take that problem and make that u to the 4th du, just like we did here, but with the correct limits of integration. So now I go back to here and say, well, when x was 1, what's the value of u going to be? 7. When x is 2, what's the value of u going to be? 19. So this will be, again, remind you, is that the same answer? 19 to the 5th minus 7 to the 5th times 1/5? Yeah. In every conceivable situation, this is either 50% of the work or less than 50% of the work. In every conceivable situation, this is double or more than double the work. Always correct, way more efficient, both can be done at the same time. But after you've done a lot of problems, this is what I do in Calc 3. I'll say, let u be this, let du be this. This is now u to the 4th du. What's the antiderivative of u to the 4th? 1/5 u to the 5th. This is what I actually do. I actually go right from here to here. Why? Because once I identify my substitution, can you all agree this is u to the 4th du?
Yeah.
And out loud, what's the antiderivative of u to the 4th du? 1/5 u to the 5th. You see what I did? I actually did the substitution. I just never physically rewrote the problem because it's right there in front of me. I don't let you do that in Calc 1 because I need you to get so good at this that it becomes second nature. But at some point you go, I can do that. It's just right in front of me. I didn't need to change everything. So I just showed you literally 3 routes, all getting to the same place. The one thing we cannot do, though, we cannot do this and leave the 1 to 2 there. Because numerically, that's something completely different. I can't have the old limits with the new variable because that is a numerical answer. Okay? So that's a reminder. I have a lot of posted notes where I'm going through this to help you guys out. This is a really cool problem because it's a nice application of the calculus we already know. This is not new calculus. Right? This is old calculus. That's why I like to start the class by doing the applications because we're not using any new techniques. We start new techniques next day, and I don't want to say they're complicated, but they're not the same as what you've learned, so you're going to be adding a lot of new tools. Okay, we're done with fluid force. Now we're going to get to one of the most common application problems, not just calculus, but in other courses. All right. You've all read your history books, and they'll talk about populations and things. And this one always makes me laugh because I remember this. In 1976, the world's population was 4 billion. You guys remember reading things like that? My kids, when they were little, be showing me, China's population is this, India's population is this, and what year will India pass up China? That was one of those questions they asked. So in 1976, from January 1st at midnight until December 31st, 11:59 p.m., the world's population was 4 billion. Because that's what it sounds like, doesn't it? The entire year. How long was the Earth's population 4 billion?
1 second.
Probably a split second. In other words, we went right through 4 billion. I don't know, where are we now? We're probably closing on 8 billion or something. So when we say world's population, we always give a number that, that's the number that it's going to be for quite a while. We'll go with that one for a while. When you drive into San Diego and it says, welcome to San Diego, and it has 2 numbers, elevation and population, and that was the population from the last census, which means it was accurate for what? About a minute? Is that number accurate in any city in the United States? No. We got to start with something. Populations grow, but they don't grow the same as money. Now, I want to remind you, periodic growth, this is money. Periodic growth, a lot of you remember doing stuff like this. This is how all money grows. P is the principal, R is the rate as a decimal, N is the number of times per year you compound, T is the number of years you compound. That's how all money grows. It's very easy. There are special calculators made, but you did this problem in remedial algebra all the time. Problem, this is not how world population grows. So if we had like a scoreboard up here, with the world's population, you'd see in the units position, it's spinning faster than you keep track of. In the tens, it's still spinning pretty fast. The hundreds is probably moving slowly, but since class started, even the thousands have probably changed. Things grow continuously. Money doesn't grow continuously. It can't. So in your remedial algebra classes, they were often saying, well, let's use the exponential growth for money, with ease. No, it doesn't work. Money cannot grow continuously. Otherwise, when you go to the bank, pray for a long line when you withdraw your money, right? Because there'll be more money when you get to the front of the line, but what about when you pay your bills? Oh, if they're slow to cash your check, then you're going to owe more money. No, it doesn't work that way. In fact, when it comes to money, okay, everyone here have a credit card? How often is your credit card compounded? It's the same as your mortgage. Same as most loans. Every second, every minute, every hour, day. Every day. So if you pay something a day early, you save a little money. You pay it a day late, day. Now, your savings account will be updated maybe once a quarter. But the compounding is still probably daily. You just won't have access to it until the end of the quarter. But money grows periodically. It grows at fixed periods. So anytime today I withdraw my money, it's going to be the same amount of money. But anytime today when I look at a population, it's not going to be the same number, is it? So I found this great account. Oh, it's awesome. And if you put your money, you're going to get $100 of interest. Think about that. You're going to get $100 of interest. If that were true, take all the money you have, open up a whole bunch of 1-cent accounts. You know, I got $100. I can open up 10,000 1-cent accounts, and each one's going to give me $100 of interest. Yes, I'll be rich by the end of the day. Is that how it works when you? Do you get a fixed dollar amount? In other words, no. What do you get? You get a percentage. Oh, okay, yeah. So if I put my money in a bank, it has nothing to do. I don't have an interest dollar amount. I have an interest rate. So the more I put in, the more I'll get out, the less I put in, and so on. Do we all agree with that? Money can only grow based on how much is in there. Even though it's not continuous, it can still only grow. So when you hear populations are growing at a certain percentage or a certain rate, that's continuous growth. So if y of t is the population, after time t. Now this is true, but it doesn't matter what I'm measuring. I can be measuring bacteria in the petri dish, and t could be measured in hours. I could be measuring the amount of an unstable radioactive material, you know, a plutonium or something, and now t is measured in probably nanoseconds. Whatever you're measuring, you have a fixed unit of measure. If it's populations of humans, t is probably measured how? Probably in years. That's the only thing you're ever going to hear. We don't talk about towns growing at a particular rate per day or per decade. Probably per year. So this is general, but think people for now if it helps you. So y of t is the population after time t. dy dt, that's a derivative. But we have to understand what that means. A derivative is the instantaneous rate of time, or rate of change, not the average. When you're driving in your car and you go from point A to point B in a certain amount of time, you can tell me your average speed. But how fast were you going right at that moment in time? That would be your instantaneous rate of change. That is a derivative. Okay? So dy dt would be the instantaneous rate of change of the population at any moment in time. If my population were growing at a constant rate. Now this is one of the great deceptions, that we're never really told the truth when it comes to the applications because it's too much to bear. But when we talk about a town or a country or anywhere growing at a certain rate, is that rate forever?
No.
No, it's always a short, finite period of time. Always. It's not possible. In fact, if it were possible to grow forever, I always have fun with the bacteria in the petri dish, right? We say the bacteria is doubling every 4 hours, maybe. So that means after a certain amount of time, it's going to crash out of the petri dish and eventually take over the floor and take over the building and take over planet Earth. Or what's the other option?
Reaches a limit when it runs out.
And they all die, yeah. Because there's not enough room and there's no food. In other words, it will grow at that rate for a finite fixed period of time. It can't grow forever. So populations can grow at a certain rate, but not forever. And that's absurd to think they can grow forever, because we'd run out of resources. We'd run out of space. Right? It can't be infinite. So when we do this problem, let's say for a finite period of time, my population is going to grow at a constant rate. Let's call that rate k. So the rate of change of the population, and by the way, think percentage. If I said my population was growing 3% per year, that would mean k is 0.03. Why? Because the rate of change is exactly 3% of whatever the current population is. When you put your money in the bank account, you're going to get 3% interest. You're going to get 3% of the amount that you put in. Everybody cool with that? That's a pretty simple concept right there. So this is the universal population growth equation. This is always true, again, for a finite period of time. I can't have k be variable because I won't be able to come up with an equation. Now, What is my dependent? What is my independent variable? What is
We
the,
just had it.
Is population.
the dependent is population, the independent is time. How do you know that?
Because calculation changes according to time.
Well, because this one's on the bottom. The independent is always here, the dependent is always here. And that's absolute across the board. So when I'm doing my integration, I have to integrate with respect to time. How am I going to integrate with respect to time? That's not going to work. I move the y over here. What if I rewrite this as 1 over y dy dt equals k? Oh, okay. Now, if I integrate both sides with respect to time, now we're getting back to the substitution problem that we learned in Calc 1. Again, I remind you, this always confuses people the first time they see it. When we're doing, let u equal whatever it is, and then we say du dx, is the derivative of whatever it is. Now we're going to integrate both sides with respect to x. Du dx integrated with respect to x is the same as du. Not because things cancel, because du dx is not a quotient. Du dx is one function. Okay, it is one function. But when I do my substitution and I change it to u, there are no more x's, are there? There's only u's. The integration of du dx with respect to x is the integration of du, because what's the antiderivative of du? U. Now I'm right back to where I started, aren't I? When I integrate du dx with respect to x, I have to get u back again. But the only way I can do that is if this is the same as this, because there are no more x's in this statement. This is huge, and it hurts our brains at first, and you won't see the absolute, definitive, perfect explanation finally until about 3 weeks left in Calc 3. That's when we do the absolute thing, and it actually involves matrix algebra. It's pretty heady stuff. But for now, what does the thing on the left become? When I integrate dy dt with respect to t, that becomes dy. There are no t's in the statement. There's only y's. What's on the right side? There's no other way of doing this. You're not canceling. You're integrating a function with respect to a variable, but this integration is the same as this integration. Because when I go back, this is just going to give me u again, which is how I started the problem. I have to get back to u by integrating. 1 over y dy. Do we know that antiderivative? What is it? Log.
Y.
How about absolute value y? Which, by the way, we're going to ignore it because y can't be negative, but we know that's the right antiderivative. What do I have on the right side? K is a constant.
KT.
KT plus, call it C1. Which makes me think maybe there's going to be another C somewhere. Now, do we agree that because y is population, I can ignore the absolute value in this case? The absolute value is necessary if that value could ever be negative. Y is the population. Y can't be negative. So in this case, I can ignore the absolute value. I'm trying to find the value of y. I have log y. So exponentiate both sides. Then y will equal what?
E to the KT plus C1.
Now, according to rules of exponents, question. Can I do that?
Mm-hmm.
C represents an arbitrary constant. C can be any real number, including 0. C can be anything. I now have e to the arbitrary constant. Can that be any real number?
Yeah.
Yeah.
Any real number? Are you sure?
No.
Can it be negative?
No.
C1 can be negative. Can e to the C1 be negative?
No.
No, so this represents only a positive number. It represents any positive number, but it's definitely positive. You guys with me on that? So let's call that, I don't know, how about C2? Okay, so here's what we got so far. We have y of t equals arbitrary constant times e to the kt. K, by the way, is known. Or it can easily be figured out within the problem. K is not a variable. K is my growth rate.
K is just some constant.
Yeah, if I said my population was growing 3% per year, then K is 0.03. K is the rate of growth. Now, what if I don't know the value of K? K is actually not very hard to figure out. I'm trying to find the growth rate of a particular area. So I take the population today, and then I take the population at some fixed point in the future. And then I can figure out K. By the way, that's what you actually did in baby algebra. You did the exact same thing. I just have to measure it today, and then again in the future, and now I can tell you exactly what the value of K is. By the way, notice that my formula is an exponential function. I remember teaching calculus a number of years ago. It was a higher level one, and I had students say, why is it that everyone says that population growth has to be exponential? Why can't it be something else? I said, that is a good question. Everybody knows that populations grow exponentially. Well, why do we know that? Because the population can only grow based on how much is there. We do know that. That's easy. I just proved why it's exponential. Because we just integrated this, that's what we got. We didn't get that because I told you that's what we got. We got that because all populations can only grow based on what's already there. You don't say a town is growing 50 people per year, but the town only has 2 people in it, right? No, it doesn't work that way. Your money doesn't grow $50 a day. It grows based on percentage on what is there. Now, let's finish this because we know the value of C2, believe it or not. What did I do? Here it is. I said, this is a hugely important problem, but it's actually one of the easier problems from a calculus standpoint. Now, at time 0, I'm measuring the population. I want to find out what's the population in San Diego at some fixed point in the future. Don't I kind of have to know what the population today is? Doesn't really help me to know the growth rate if I don't know how much. It'd be like saying, oh, how much money is in your account? I don't know. I didn't pay attention to how much I put in. Right? So think of the starting population kind of like your principal. So at y of 0, that would be today. We often do that. In any math or science course, when you see a subscript of 0, it always means the same thing. It always means initial condition, starting point. That's my population right now. If I plug that into that equation, what am I going to get?
E to the 0, yeah.
Wait a minute. Didn't we say C1 represents any real number and e to the C1 is just some other arbitrary constant? Is e to the C1 an arbitrary constant?
No.
No. It actually isn't an arbitrary constant. We just figured out that e to the C1 is your initial population. That's kind of cool, by the way. So now we have the final formal version of the equation. This is the universal equation that governs all population growth. Starting population, e to the kt. Now, if I know my starting population, I can tell you I can predict what the population is going to be. This is, you got to be really careful. You guys have all had this. What will the world's population be in 3 years? If you can tell me that, you can save me a lot of stress. And just go ahead and tell me what the Super Bowl score is going to be in a couple weeks so I don't have to get all worried about it and lose some sleep. You do realize it's impossible to tell what the world's population is going to be, any more than you can tell what your investment is going to be in the future. No, that's not how it works. We say that a population has been growing for this rate for a particular time. And we preface it by saying, if it continues to grow at that rate, you got it? Then what will the population be in the future? Is that a valid question? Yes. If it continues to grow at that rate, is there any guarantee it's going to continue to grow at that rate? No, but if we have a history that has grown at the same rate for a while, then for a short period of time it is reasonable. It is totally reasonable to use that rate of growth. Because you got to have a starting point, right? It's not going to be a guess. Now, are there things that we actually do know the rate exactly? Yes. We do know some things exactly. For example, when something dies, it decays at a particular rate, and the rate's not going to change. I've got you guys ever seen crystals, like how they grow? Kind of a cool thing. It's growing at a constant rate, and it will literally do that, as long as there's room. That's not a finite temporary thing. It's growing at a constant rate. When things die, they decay at a constant rate. We know this. This is how they do carbon-14 dating, right? Because we know the rate of decay. But that's for really, really, really long. Okay? So, now, this is growth rate. What if k were negative?
That'll
It
be
won't
decay.
change.
then it would be decay. So the equation for growth and decay is exactly the same. It's just is K positive or is K negative. It's actually that simple. So things grow, things decay. It's just the exponential in reverse order, because isn't that just as valid? So what you did was you said things like, when will the population double? Okay? When will the population double? Well, when will y of t be 2 times y0? Do you agree that's when the population will double? This is not new stuff. This is not calculus. This is stuff you guys did a million years ago in baby algebra. What's the first thing I can do here?
Divide both sides by.
Hold the phone. Oops. Hold the phone. So are you telling me that it doesn't have anything to do with my starting population? Yeah. So Chase and I both found this account that gives a ridiculous interest rate. And I was kind of broke, so I put $1 in and he put $1 million in. Whose money's going to double first?
At the same time.
The exact same time. Who's going to reach $2 million first? Well, he will. Yeah, that's where it matters how much he deposited. But if we're putting it in the same account, they're going to double in the exact same amount of time. That confuses us at first, right? Because that seems like it should matter. No. How long it takes to double is independent of the starting amount. It only matters on the growth rate. So doesn't this mean that log 2 equals kt? So t equals log 2 over k. This is an equation you guys did back when you were in baby algebra. So if I said tripling time, log 3. Now, what if? What if this k is negative?
That'll be decay.
Then it'd be decay. And so instead of doubling time, what would I be asking for?
Half.
Half.
That's what half-life is. It's the exact same thing. Well, so what would the half-life be? Same thing. Same equation. Log 2 over, in this case, negative k. Because k was negative to begin with. So the doubling time and the half-life are the exact same formula. Everybody got that? And it should make sense. If I'm growing, when will I be twice as much? If I'm decaying, when will I have half as much? Because it's like saying that much long ago I had twice as much. That's kind of cool, isn't it? You go, wow, the calculus explains all of this stuff. Now, this is the simplest problem there is. Okay? It's not the only problem there is. So, if things decay at a constant rate or they grow at a constant rate. Now, this is one of the biggest problems we have with things like dating things. It's hard to date something that has died recently. For example, if I wanted to find out, there's a dead animal, I don't know. There's something we found and we're trying to figure out how long ago it died. As long as there's something still there, we can look at the degradation, we can look at the decay and things like that, because we can compare it to, in other words, when we're measuring the carbon-14, we can compare it to a living thing. You know, how much carbon-14 does the living thing have and how much does this one have, and we can actually work backwards and do that. As long as there's something alive. When does this become a problem?
When things are extinct.
Something's extinct. Yeah, you have nothing to compare it to. So one of the biggest problems and biggest dilemmas that we face is trying to date things that aren't there anymore. We can't. It's pure guesswork. I've seen all the Jurassic Park movies over and over again. I love them. You know what's funny? When I was in school, elementary school, it was taught that people walked with dinosaurs. You know why? Because every major dig site on planet Earth, everywhere they ever found fossilized remains of dinosaurs, they found human remains and human footprints. That's something they don't tell you. When I was in high school, dinosaurs lived tens of thousands of years ago. When I was in college, they lived 1 million years ago. When the first Jurassic Park movies came out, they lived 35 million years ago. But the most recent Jurassic Park movies, they now live 150 million years ago. No science has changed. We have no new discoveries. And I'm always saying, how do dinosaurs keep getting older and older and older and older? Because what are they basing it on? Oh, fossilized records. How much of a dinosaur is in a fossil? 0. What's a fossil?
Rock.
Yeah, the dinosaur decayed and this formed around it. There is absolutely nothing, not even at the subatomic level. There's no DNA, there's nothing there. There's only a picture. I mean, you could just make one up and say, this is my fossilized dinosaur. The problem is, you can't date something that isn't actually still alive because you have nothing to compare it to in terms of the carbon-14 degradation. So a number of years ago, I can't remember what year, I just remember it was such a cool thing, they found a frozen woolly mammoth. You guys remember that? You can look it up. They found a frozen woolly mammoth with undigested food in his belly. So I don't know what happened, must have been like an avalanche or something, you know, and flash frozen. The problem was, I believe they thawed out the woolly mammoth. That was the mistake. And then immediately it, it decayed and everything else. You know, I don't think they realized that if you thawed it out, that's what would happen. It's like, you know, it aged really quickly. But the fact is, could they put a date on how long ago this thing got froze? Think about that logically. Could they put a date on how long ago? It was frozen for who knows how many years. Well, how much did it decay during the time it froze? None. Yeah, so in other words, it was perfectly preserved, and there aren't, last time I checked, there aren't a whole lot of mammoths running around. You know, I've seen the Ice Age movies. I think it's cool they all talked, but you know, I have a lot of kids. I've seen everything. But the problem is we say this is really cool, but our hands are tied. We don't know what to do with the science. It's unfortunate. And I don't like picking on my science friends, but I always thought, I'm a math person. It is or it isn't in math. You can prove things are true or false. When I went to school, I did my first round of graduate work at UCSD, and I took some chemistry classes because all of my best friends were in the chem department. At UCSD, that some of the top researchers in the whole world, and the richest chemist who ever lived, the guy that invented the polarized lens, he was one of the instructors. He was a billionaire. He just taught for fun. He was terrible. I took one class. Oh God, he was awful. He drove a solid gold Rolls Royce. Solid gold Rolls Royce to school. Who does that? Yeah, this guy was filthy rich. He invented the polarized lens and was, you know. But do you know what they taught as absolute fact? Absolute fact. Across the board, that the periodic table would eventually be completely filled in. That was absolute fact. And then my best friend did his PhD at UCSD in chemistry, and about 10, 15 years later he says, no, we now believe that we got holes everywhere. And then I believe shortly after that they did find one more element. In other words, what's absolute fact seems to change every few years. It's like, everything that we've ever, you know, in science, absolute fact changes once we find something new. In math, it never changes. Math is just so much safer to me for that reason. But this will work for short periods of time really easily. Now, my absolute favorite application that exists, and this is one I'm doing in DiffyQ later on today. All right. Imagine we are in a situation in the classroom. First, and maybe the most important, we are in a constant room temperature environment. This is actually very important for the mathematics. Okay, the room temperature is usually referred to as the ambient temperature. So you'll hear the word ambient and go, what does that mean? The room temperature, I cannot be in a situation where the temperature fluctuates. So I'm in a constant room temperature environment. So I bring the hot cup of coffee and I set it on the desk. Tell me what immediately starts to happen.
The desk absorbs the heat.
Well, think about the coffee though.
It gets colder.
It's not getting warmer? It's getting cooler. What if it's a really hot day? Yeah, do you all agree it probably gets cooler? Okay, so let's look at what this looks like. All right, whatever the ambient temperature is, (75 degrees, whatever. This is the constant room temperature. At time 0, I'm putting a very hot cup of coffee in the room. And you said that it cools. So eventually it's going to reach room temperature. And eventually, therefore, it'll be cool to the room temperature. We have a problem. Because, and eventually it's going to get colder and colder and colder. It's going to freeze. It's going to get colder. It's going to start approaching absolute zero, in which case all molecular movement within a radius that is expanding will cease. Pretty much, eventually planet Earth will be a frozen ball of ice because of my indiscriminate use of coffee. Or not. You see, if the temperature reaches room temperature, then it means it has to keep going. Because this is a rate of change, and rate of change is differentiable, it can't have a jagged edge. That's not possible mathematically. It violates laws of physics. So maybe it's asymptotic to the temperature. By the way, those are the only two options. It's asymptotic to the room temperature. Ooh. Now, since we measure temperature typically, with like a thermometer that's usually not very precise, right? I might get 1 decimal place. How many, when you take your temperatures, ever, have 2 decimal places? Really? Right? You're lucky if you have 1 accurate. Does this seem like it might be a better fit? So maybe we don't all freeze? Can I ask the question, after any amount of time, how warm will the coffee be? Can I ask that question? Sure. But I need to know one thing. I know how warm it was when I set it down. I have to pick an arbitrary point in the future and measure it again. That will determine its rate of cooling. You understand that? We said the same thing with populations. I have today's initial population. I can measure it again in a year, and now I can easily calculate the rate of growth. That's actually trivial. Right? We did the math earlier. So the question is, I want to come up with an equation that governs how hot this cup of coffee is. Well, this is clearly decay. Now, there's an interesting thing that a lot of you are probably very well aware of. Let's suppose that this is time, and this is money, and this is how much I just spent on a brand new car. Doesn't the same thing sort of happen with a car? Now, it can't be linear, because that would mean eventually a car's worth a negative amount of money, and in fact, now you owe more money than the country is producing. No, but same thing. In fact, do you know what the asymptote is? The DMV sets that. How many have an older car right now? Do you notice when you pay your registration every year what's happening? That there's part of it that goes down every single year. Every single year go down, because they're telling you your car's worth less and less and less, but it's never going to be worth 0. And the amount it goes down is not a constant. If you actually started charting it, it would look more like this. That's by design. That's called, you said, depreciation. Depreciation is a form of decay. In that case, it's a little more jagged, but it's the same idea. So when is this thing cooling its fastest? At the beginning, when it's at its hottest, when the difference between the temperature and the ambient temperature is the greatest. So if I took T of T, we'll call big T the temperature and little t the time, and I subtracted the ambient temperature, okay, when is it cooling the least? When that quantity is really small. Is everybody okay with that? It's almost the same equation as population growth. It's a little more complicated. So this is the rate of change of temperature with respect to time is a constant multiple of the difference. Is that K going to be positive or negative, do you think? Yeah, if it were positive, then that means it would be heating up. So it's going to be negative. It's probably not huge, but it's going to be negative. Everybody with me on this? Okay, we're going to actually come up with the equation. This is called Newton's law of cooling. And it's a very powerful thing. We actually use this, and I'm going to give you several examples where this is used in real life. So what do I need to know? Well, obviously I need to know how hot is the cup of coffee when I place it down. That's not really complicated, right? It's 140 degrees, it's too hot, I'm going to wait a couple minutes. I know what the room temperature in the room is. What I don't know is how fast it's cooling unless I take a reading in the future. You with me on that? And we'll do that next. But let's see if we can solve this sort of in general. So just like before, throw that in the denominator. So I have 1 over, I'll just call it big T minus A. It's understood this is T of time. 1 over this dt equals K. So now I'm going to integrate both sides, and I'm going to integrate both sides with respect to time. And so just like with the population growth, d big T dt is the same as just saying dt. This presents a very simple differential equation at this point, or excuse me, very simple integration. This is the differential equation. Now that term always scares people, and again, I remind people, do you know what a differential equation is? It's any equation involving a derivative. That's it. You did that in Calc 1 when you solved things. This is called a differential equation, and our goal is to solve it. It's not that complicated. 1 over a is a constant. Isn't that going to be a log again? Well, if it were this, wouldn't it just be log t? So it's just log t minus a. And again, I'll put the absolute value. And that's going to equal what? Kt plus again, C1. And just like before, what are we going to do? How did we do it last time from this point?
Change it to exponential.
Yeah, we exponentiated both sides. I'll put it up here. So that t minus a is e to the kt plus c1. Now, I got a lot of constants in here. A is given. K I have to calculate, but I will be able to calculate K. I don't know what C1 is, but I have a feeling C1 is going to involve an initial condition like it did with population a moment ago. Okay? So let's do like we did before. And let's just call that, how about C2, e to the KT. So I have an A that's given, I have a K that has to be calculated, and a C2 that I think I can figure out. So right now, let's get the t by itself, shall we? So t as a function of time is then a plus C2 e to the kt. At time 0, that's how hot the cup of coffee is the moment I place it down. That is known. You measured that. You wouldn't do this problem if you didn't know that. That'd be kind of like saying I want to figure out the population in San Diego for the next 10 years, but I don't know what it is today. No, I have to start by knowing what it is today. What does this equal? It equals A plus C2 e to the, oh, it's just A plus C2? Oh, so that means that C2 is T0 minus A. Ooh, remember I said it probably involves some initial condition? So right now, we haven't even started doing anything. We haven't done a single calculation. At this point in the game, I can say with certainty, this is A plus T0 minus A, which is a constant. That's a given constant. That is actually essentially a given constant, isn't it? Because I know T0 and I know A. E to the KT. The only thing I don't know is K. So we're going to do a problem where we have to figure it out. Can we go ahead and prop that open again? I think they're done with the dumping. Yeah, you guys with me so far? This is Newton's law of cooling, and I'm going to talk about all the situations where this actually comes into play. So I give you a situation. I need to tell you the ambient temperature. I need to tell you the initial heat. And someplace down the road, we did a measurement. Okay? We did a measurement and said, here's how hot it is now. Okay, so let me start with a fairly simple problem. This isn't the final. No. The final thing is I need to have the K. I need numbers. I need numbers in there. But this is kind of where we can jump to, literally. All right, so let's say we have a metal sheet. You left it in the oven, is 320 degrees Fahrenheit. You have a really hot metal sheet, piece of metal. Okay? You put it in a room with constant temperature, let's say 64 degrees. Okay, we know it's going to start cooling down. Do we know how fast it's going to cool down automatically? See, you say, well, a cup of coffee, isn't it automatically going to cool at the same rate? What if you ever go to the coffee places that have those big old ginormous mugs that almost look like, cereal bowls? That's going to cool probably faster. What if you put it in a well-insulated thermos? It's going to barely cool down at all, isn't it? So the same coffee is not going to cool at the same rate. It depends on what it's put in. So that's why I have to take a measurement in the future, because it's not always going to be the same thing. Okay, so I put in this constant temperature of 64 degrees. Now, let's say in 6 minutes, it has cooled to, let's say, 128 degrees. So I have it's sort of like you have the metal pan in the oven. You put it in your kitchen, you set it down on the counter, and 6 minutes later it's 128 degrees. It's not going to be room temperature in 6 minutes, in all likelihood, right? But it is cooling down rapidly because that's a huge difference in temperature. Okay? So there's several questions. One question is, can we come up with an equation that tells us the temperature at any given time? Then I can ask things like, well, then how warm will it be in 10 minutes or 20 minutes or 30 minutes? I can say, how long will it take before it's down to 80 degrees or 90 degrees? Do you guys remember doing stuff like that in baby algebra? In baby algebra, you invested this much money at this interest rate for this time. How much will you have at the end? But then we could say, how long do you have to leave it in there before you have this much money? Do you remember doing things like that? In some cases, the thing you had to solve for might be in the exponent. A little more work. So let's take this information and let's put it into here. Let's identify what we know. Okay? What do we know? Well, what is A? 64 degrees. What is T0?
320.
And what's 128 then?
That is
T6.
T of 6, good. By the way, does it matter what unit of time I use? No, but what would be the most logical in this case? Minutes. Yeah, you could use hours, but then you'd have fractional hours, and I think the arithmetic gets kind of yucky. I would use minutes just because, if I said in 6 hours, yeah, I'd use hours. But in 6 minutes, there's no logic to using 1/10 of an hour. It's not wrong. It just makes all the numbers a lot uglier. Okay, do we all agree? This is what's given. Okay, this is how I compute K. So, T of T in general is 64 plus, what's 320 minus 64? That's the hard part.
what did you say?
256.
Okay? Okay? I know this is true. I have no idea what K is. But this is going to help me find K. If I gave you a different temperature, it would give me a different cooling rate. Agreed? So, what is T of 6? Well, it's 64 plus 256 e to the what?
So the
6K.
To the
6K.
6K. Good. I really want to say K equals. Question?
Could you not find the value of K by subtracting 320 and 128 and then dividing by 6 to figure out how fast it cooled over those 6 minutes?
Because this is in the exponent, I kind of need to isolate this guy. Yeah, because the value of K is going to be a logarithm.
Oh,
You see?
right.
Yeah, because of where it's up there. So I do want to get the E by itself. So why don't this all equals 128. Sorry. So throw the 64 over, and I'd have 256 e to the 6K equals 128 minus 64. Throw the 256 over, and I'd have e to the 6K equals, I think that will be 1/4.
Yes.
So far, so good?
Yeah.
So therefore, what does 6K equal? Log of 1/4, which will be a negative number, by the way. So what does K equal? 1/6 log of 1/4. Yuck.
Well,
Is that a positive or a negative number?
positive.
Negative.
Well, log of a number between 0 and 1 is negative, isn't it?
Right.
Is that a good thing that it's negative?
Yeah.
Yeah, because if it was positive, that would mean I'm heating up. So this is negative, so I am definitely cooling down. Okay? So where does K go? Where is it? K goes right here. Now, here's the universal mistake that people make because they're not thinking about the big picture. That let me give a decimal approximation of K. Okay? Something that this is an absolute in all math and science. You never approximate a coefficient, ever. You approximate final answers. Think about something as simple as the area of the circle. What's the area of a circle? Pi r squared. So I give you an r and I ask you for an answer and you give me some number of pi's and you hit your calculator and you give me a decimal approximation. Does anyone start by approximating pi and then multiplying it by r squared? No, because it means that from after the second decimal place, every number you write really isn't very close. In fact, if you have a large r, that means even your first digit might even be correct. In other words, your answer is complete garbage at that point. You would approximate a final answer. You don't approximate the pi, right? If I have a line as root 2 times x, I don't approximate the root 2. It shows up everywhere. If I want to approximate my answer, I approximate my answer. If I approximate the k, it will be impossible for me to give you a correct answer. I can get really close, but I can't give you a correct answer. And here's the worst part why you never approximate the k. Where does k live? In the exponent. If I change the value in the exponent, that gets magnified really big. It really has now a gargantuan effect on the error. So what do? K is going in the exponent. I'm going to have an e to the log. Isn't e to the log really friendly? Right now, what do I have? I have e. Let me write it out. What if I wrote it like this? E to the, first of all, I'm going to write it as t over 6 log of a fourth. Agreed? So what if I now wrote it as e to the log of 1/4 rules of exponents? Isn't that what it does? So this is what I love about this. This is e to the log of 1/4 raised to the t over 6 power, which is what? 1/4 to the t over 6 power. E and log undo each other. This is how, in every math class you'll ever have the rest of your life, how you're supposed to do this. Most people will approximate the k and then give me answers that are relatively close to the right answer. I don't want relatively close. I want exactly the right answer. There's no place in this problem where I need a calculator so far. Again, I'm just using rules of logs. Because my k lived in the exponent and k already had a log, I know everything's going to undo each other. So now let's go back to here. Can you now tell me t of t exactly? Yeah, it's 64 plus 256 times 1/4 raised to the t over 6 power. That's pretty clean. I think I did it right. I'm pretty sure. Now, by the way, I know there are commercials that have stolen this from me, but I've been using Pretty Sure for years and years. So I'm pretty sure that that 10-story house I built in my backyard yesterday is not going to fall down, right? I'm pretty sure that even though I made up all the numbers on my tax return, I'm not going to get audited. And of course, my favorite, I'm pretty sure that stray dog foaming at the mouth doesn't bite. This is mathematics. There's no pretty sure. There's certainty or there is not. I need to be certain that I did this right. Do I have a way of checking this?
Plug in T of 6.
Okay, let's take the given information. Let's start with 0. At time 0, what would I have?
T is 0.
This would be 1/4 to the 0, which is 1. Would I be at 320 degrees?
Yeah.
If I put a 6 in here, I'll be 1/4 to the first power. So 1/4 times 256, that's 64 plus 64. That works, but here's the best one. As t grows without bound, what's happening to this? As t grows without bound, it's approaching
64.
this term is approaching.
That term is
As t grows without bound, 1/4 to the bazillionth power is approaching 0 rapidly. If this is approaching 0, then this quantity is approaching 64, which is the
room temperature.
Room temperature. In other words, it's asymptotic to room temperature. That may be the most important check of all. So does that work consistently?
Yeah.
Yes, as T grows, that is going to approach room temperature. So if I said, what is the limit? This is huge. What is the limit as T goes to infinity of T? If you did it, it should be 64 degrees, because this is approaching 0. And that's what it had to be. So, do I have faith that that's correct at this point?
Yes.
Yeah. So, this is the general equation that is governing this. So, I'm going to ask you a simple question. How hot is it going to be in, I don't know, how about in 12 minutes? It went from 320 to 108 in 6 minutes. How cool is it going to be after 12 minutes?
We'll just plug in 12 for the value of T and then solve.
Okay, let's do that. I'm going to erase, I think I can erase this. My beautiful picture here. What is T of 12? Well, it should be 64 plus 256 times 1/4 to what power?
2.
2.
To the second power. And what does this give us?
80.
Is it exactly 80?
Yeah.
Yeah. Do we need a calculator? Well, if I ask you in 9.3 minutes, yeah, I probably need a calculator. Can I ask a question like, how long will it take to reach a certain temperature?
Yes.
Yes. And in that case, you'd be solving for the T that lives in the exponent, which means your final answer would be a logarithm. That's the ickiest one. Even going back to baby algebra, how long do I have to leave my money in before it's worth this much? You had to solve for an exponent, it was a logarithm. People don't like that one, right? Because now I have to use a calculator. But this problem is pretty clean, isn't it? Newton's law of cooling. So, where is this used? Well, it's a little bit tricky because, again, if I said, what's the temperature in 3 days? Isn't it going to be 64 point something, 64.01 or something like that? You agree it's going to be something really close to 64, but my crude measurements, I have a little cheap thermometer, am I going to see the difference between this and 64 degrees? No. So, if water freezes at exactly 32 degrees, I don't know if it does it exactly. Let's suppose water freezes at exactly 32 degrees. So you're having a big party for the Super Bowl and you need lots and lots of ice. And so of course you set your freezer to 32 degrees and you put in all your ice trays. And then you wait a couple days and then you go to pull out all your ice trays. What are you gonna notice?
It doesn't melt it.
None of them are frozen, not one of them. Why? 32 is the asymptote. None of them are 32. They're 32 point something, but it's not mathematically possible unless I wait till infinity passes away. So, do you set your freezer at 32 degrees? No, you set it much colder than that. Otherwise, nothing would freeze. I'd say that laughingly. If you set your freezer, so I want to boil some water, so I set the stove to exactly 212 degrees. My water's never going to boil, is it? I have to set it above boiling, because boiling would be the asymptote. Remember, the picture is actually quite accurate. That we forget that sometimes. So, now there's a different question. All right, because I do most of the cooking for my family because my wife works up in North County and she's home later. So I got some frozen chicken and a lot of frozen chicken in the freezer. It's one of the few things I'll freeze. So I take out the frozen chicken and I put it on the counter in the afternoon. And my kitchen stays relatively the same temperature. Tell me about that frozen chicken. What's going to happen? It's going to start
Melting.
warming up.
Warming up.
Yeah. And eventually it keeps warming. Gets warmer. Gets warmer, warmer. Eventually it's going to burst into flames. Eventually it's going to get hotter and hotter, go supernova, burn up all of the oxygen in the atmosphere, and then this whole planet is a ball of fire. Or maybe it doesn't get that hot. Maybe room temperature once again is asymptotic. In other words, the heating is exactly the same as the cooling. The room temperature is the asymptote. It's the limit. It's not the amount it's going to be. But for all practical purposes, right? When I'm measuring, if I'm within a fraction of a degree, it's there. Do you agree? It's there. Your temperature in your oven, you set it, is it that hot the whole time? No, it's fluctuating constantly. That's just kind of the area it's going to be around. Okay, where this one is often used. This story sounds terrible, I know always. Where I live on my street, we've actually had 2 elderly shut-ins die. 2 gentlemen, they were widowers, like 90 years old. They died. Rich, full life. And one of the neighbors, you know, he would go check on them regularly and sometimes bring food over, and he found them. Both people were found by the same neighbor. That's not a job I would want. So one lived on one side, one lived on the other. They died several years apart. Point is the house was essentially a constant temperature environment. The coroner goes in there and they need to determine time of death. Is that possible? If we make a few assumptions, first of all, the constant room temperature is not really that difficult to maintain. A healthy person generally will have a body temperature in the range of what? 98-ish degrees. Do we agree with that? By the way, don't tell me 98.6. They stopped using that about 30 years ago. Now that the norm is 98.3. And my temperature will only measure 98.3 if I'm feverish. My temperature is generally about 97.5, which is hard to believe because I emit, you know, heat. My temperature doesn't reach 98 ever. Like I said, unless I was sick, which doesn't ever happen anyway. So yeah, it never reaches 98. But they'll use 98.3. Why is that important? Because we find the person now. Are they going to be warmer or cooler than 98.3? Cooler. So we take a core body temperature relatively soon, expecting it to be higher or lower? Lower. And we can work backwards. This is why this map is so beautiful. It's so cool. Okay, here's the room temperature again. We will assume this was when they died. That was when it was 98.3-ish. We're expecting to see this. We find them here, we measure them here in order to figure out what the K is so we can work backwards time-wise. Isn't that cool? Mm-hmm. Is it absolute exact science? No, because I said we're making a few assumptions. We're assuming that their core temperature was relatively normal. What if they had a bad fever or something? We're making certain assumptions. The other thing is you can't wait too long because the ability to measure temperature accurately. Now think about that. It might take a really long time to have a 1/10 of a degree degradation if I wait too long. Does that make sense? So if done in a relatively short period of time, I can do this. Now, the person was out hiking the wilderness. We haven't heard from them in a while. We find them, they may, attacked by a mountain lion or something. Can we figure out the time of death? Why?
It's not like a constant ambient temperature.
Because they're outside. Temperature fluctuations are too wild. That won't work for that. It only worked for the constant temperature environment. Okay, everybody cool with that so far? Now, where else is this used for? This, I can only suggest it here. The mathematics to do this, I learned is one of my last upper division math courses in college. It's called partial differential equations. It's actually one of the more scary courses. But imagine right here, my table here, imagine it's a table, a heat source. How many here ever do any grilling? You have a barbecue. And of course your barbecue is absolutely uniform. Every single point on your barbecue is always exactly the same temp, right? No, there's no such barbecue, right? There are hot spots, there are cool spots, everybody knows that. So on this surface, imagine every point on this surface has a different temperature. Now, this is beyond us because that means there's more than one independent variable, but just stay with me. I could come up with an equation that governs the temperature at any given point. It's actually not that complicated. It's an early Calc 3 problem. But it's the differential equation. It's the rate of change. If I have rates of change at every point, heating and cooling down, that's a little trickier. So my brother is a very successful contractor, and he used to build new homes, and for many years he's done primarily insurance restoration. So when you have a flood or a fire at your house, he's the guy that comes in and saves your bacon and does an incredible job and makes everything perfect again. Fires are some of the biggest money things. Now, how many here are homeowners? Anybody here paying a mortgage? People say that you can't cheat death and you can't cheat taxes. I don't know. I think you probably cheat both. But there is one thing that is not possible in the United States. You cannot own a home in the United States without fire insurance. Yeah. So you say, I don't want to pay fire insurance, and guess what? The bank's going to take your house. It's strange enough. You can miss a mortgage payment, but if you can't drop your fire insurance. Fire insurance, why? because your house is worth a lot of money. You have to have, you don't have a choice on that one. You have to have fire insurance on your home. Now, life insurance, I love talking about life insurance. Life insurance they're the wealthiest companies on planet Earth, and it's not really anything close to it. If every American who died, life insurance companies could pay all the policies, which would be in the, I don't know, range, the quadrillions. Life insurance companies are worth a lot more than entire countries are worth, which is why life insurance is outside the law. Did you know that? Life insurance benefits cannot be taxed. It cannot be touched. That's why you have to make sure that you have a good will to leave to your dependents to make sure. But insurance in general, and when I say outside the law, I don't mean they're doing things illegally. I mean the government can't step in and tell them what to do. They have way too much power because of their sheer value. Fire insurance is critical. Now I point that out because my brother does a lot of things with fires. Now there's only two ways a fire can happen, and they both begin with A. Accident or arson. And it's the insurance company, they go in and they figure out which one it was. And they absolutely always figure out which one it was. So it's a big building and it's burned out. This is the beauty of the mathematics. I can't explain it right now. But using the differential equations, you can find the point in space, literally, that the fire started. You can actually look back heat signatures and things you can find. So they find a little spot on the wall and they see all the burnt out wires and things like that. It was just too old. Clearly there was an accident there. And this is one of my favorites. My brother was telling me it was a big job he lost. They found literally almost microscopic remnants of the gas-soaked rag. You couldn't even see the rag, but they could find it using their spectral equipment. They found remnants of the gas-soaked rag on the floor. So people went to prison. Yeah, insurance fraud. There are crimes you can get away with way easier than insurance fraud. You're not getting away with that one, period. They're just too powerful. So now it's arson. So if it's accident, then he comes in. But it's all based on versions of this in 3 dimensions, is what I'm saying. Isn't that crazy? Now, you aren't the person doing this, but you will understand, if you continue studying mathematics, you'll understand the mathematics involved, and it won't seem all that complicated to you at some point. Now, I have fun with this one because it happened to somebody I know. Anybody, I don't want to embarrass you. You're going through the drive-thru, you're getting your coffee, maybe it's a nice day, so you're wearing shorts, and you're getting your coffee in the styrofoam cup, and you decided to put it between your legs. Yeah, I have a friend whose wife is a PhD professor at San Diego State and got 3rd-degree burns because she put the coffee between her legs in the drive-thru, and it spilled all over the place. But there is a certain McRestaurant, I won't mention any names because I don't want to get sued, that multiple lawsuits, and they paid out millions and millions of dollars in lawsuits for exactly this, because they were known to serve their coffee. They would serve coffee at 140 degrees. And I have coffee every morning. You can't drink 140-degree coffee. But they would serve their coffee at 140 degrees in styrofoam cups, and people were getting burned left and right. It seems to me you kind of brought that one on yourself if you're getting burned. But the problem was they were paying way too many lawsuits. So they had to figure out, okay, after we brew this pot of ridiculously hot coffee, we need to figure out how long we should wait. Does that seem like an ode to serve the coffee so that it is a temperature that is more viable? You can't brew the coffee at a cooler temperature. It doesn't work that way, right? The water's way too hot. So they figured it out, and now there's a timer and the thing. So when you go and you get your coffee at the McRestaurant, you're probably not going to scald your legs like you would have before. You still might burn yourself. But now, it's going to be less damaging and all that kind of stuff. But I thought it was funny because the first time I read about this, it was many, many years ago, they actually credited Newton's law of cooling with the way of figuring it out. Because somebody, probably a burger flipper, said, I had this calculus class. It's a really easy way to do this. So Newton's law of cooling is basically population growth on steroids, right? It's the same sort of problem. I got a little bit more going on. So now, I want to do a really simple decay problem, just get everybody kind of used to this. All right? Let's suppose that you have a radioactive substance, let's say decays 20% I don't know, let's say every 4 hours. You have something it's degrading really, 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 really fast. Okay, are there a lot of things that decay that fast? No, but I mean, we know things that decay ridiculously fast. Unstable elements will decay very fast. So I would like to know how much of the substance there is after a certain amount of time. I'd like to know when will half the substance be gone. I can ask all sorts of questions. So let's just say, okay, you begin, let's just pick a random amount with, I don't know, let's say 1,000 milligrams. How much is left after T hours? And then we can just pick numbers for T. Do we have enough information to do this one? This one's actually quite a bit simpler than the other ones in a sense. So I know that y of 4 is going to be, now be careful, you're losing 20%. Is 20%, is that number anywhere in the problem? No. I used to teach remedial algebra, and you remember doing percent problems? Do you remember doing markup and markdown problems? Do you remember doing that? You know, the store, everything's going to be marked up 30%, blah, 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 blah. And I would show the markup and markdown problems. I said, you never use that percent. You're always using 100%. So if you have a 30% markup, you're not using 30%, you're using 130%. If you had a 30% markdown, you're using 100 minus 30%. So if I'm losing 20%, 20% doesn't show up anywhere in the problem. How much do I have in the next 4 hours?
8.8.
I have 80%. Does everybody follow that? That's the universal error we make. We're looking at the wrong number. Not how much do I lose, how much do I have? So y of 4 would be what?
0.80 y naught.
0.80 times, well, in this case, my 1,000. Everybody okay with that? Okay, so if I'm doing this, if every 4 hours I'm going to lose 20%, then could I write it like this? Y of t, I'm going to have, what did we say, every 4 hours? Okay, how do I show that? Well, first of all, every 4 hours, I want a t over 4. I want 80%. Sorry. Where does the 1,000 come in? That's just in front. Sorry, this should be, sorry, I wrote that down, t over 4. Now do a quick check. At time 0, I'm 1,000. After 4 hours, I'm 80% of 1,000. Would you agree in another 4 hours I lose another, I'm 80% of that, and so on and so on and so on? Yeah, that's it. That's pretty simple, huh? So if I said, how much is there going to be in 8 hours? $640, good. When will I have only half as much? When will y of t equal 500? That's a harder one. So I want to say 500 equals 1,000 times 0.8 to the t over 4. So that means that 1/2 is 0.8 to the t over 4. Now, by the way, if you want to change 1/2 to 0.5, but it's not going to make any difference. I now have to do a logarithm, don't I?
Yeah.
So the log of, I'll write that, 0.5 equals what? The log of 0.4 to the t over 4. Everybody remembers? You guys know the sound, right? I love doing that with logs because they always make that crushing sound. So I have t over 4 times log 0.80. Can I get the t by itself?
Yes.
Yeah, that's the easiest part. So t equals multiplied by 4 over the log. I am now 4 log 0.5 over log 0.8. There was no formula you could just start by plugging in. You got to actually solve. But was that complicated?
No.
Not really. So I could have said, how long will it take for any amount? I could have asked any amount and you could tell me. Now you get your calculators out. That might be the answer. Later on today, I want you to go down to Home Depot and get that many feet of wood. Right, is that going to work very well? You know, you show them this and they're looking at their measuring thing going, I don't see any logs on that. Spec, they might have logs on their measuring thing, but probably not quotients of logs, you know, probably not a lot of that going on. So what is this approximately? Get out your calculator.
12.425. 425. 12.425.
425?
What?
12.425.
Oh, I'm sorry. I think you said 12.425 what?
Milligrams?
So it was when, so it has to be time.
Time, sorry, yeah.
Hours.
Hours, sorry.
Yeah, we hate units in math, don't we? Yeah, this has got to be hours. Hours. So let's make sense of that. In 4 hours, I had half as much. Excuse me, I had, 80% as much. In 8 hours, I had 80% of that, which was 640. In another 4 hours, I have 80% of that, which is 512, by the way. That's in 12 hours. This is a little more than 12 hours, we're down to 500. So is that answer reasonable?
Yes.
Yeah, because I can tell you 12 hours, we're going to have exactly 512. So that makes perfect sense. Kind of nice, huh? So you have the mathematics to solve these things. The worst you're going to do is take a logarithm, but you have a calculator. Okay? So this is the exact answer. That is absolutely correct. But it is necessary to do an approximation because that doesn't mean anything to me. Right? Remember, in math or science, you always give the answer first, then give the approximation. Why don't you go directly to the approximation?
Error.
If you made an error, you're never going to figure out where it is. Yeah, you just have a wrong number with no support. Plus, you can't check it. No, you always give the answer and then give the decimal approximation if it's necessary. In math, you know, when you're finding the area of that circle and you said the area is 100 pi, you never calculated that as a decimal. Nobody cares. You said it's 100 pi. You didn't need to calculate as a decimal. But if, like I said, I'm going down and I'm getting a measurement of something, I do need a decimal value. In chemistry or physics, right, you have to give a decimal approximation to your answer, but always give the answer first, because otherwise you have no way of checking to see if it was actually correct. The problem with skipping that in-between step is if you made an error. It's impossible to find the error. All you know is that you have a wrong answer, but you can't figure out where it came from because you didn't write anything down. All right, let's go ahead and stop. Before